Hello everyone. Today I'd like to talk about tic-tac-toe. So everyone has heard about tic-tac-toe, everyone has already played tic-tac-toe, and basically everyone knows that the basic version of the game is a draw. Right? If I start wherever, I can quite easily force a draw by doing just something like this. Okay, so this is not very interesting, but if you've played a bit with the tic-tac-toe board, well, you probably realize that if you use a larger grid, then this is not a draw anymore. Okay? For instance, on a 4x4 grid, the player who starts is going to be able to win. Okay, for instance, if I start here, let's say I go here, then I go here, so here I have to block one side, and then you lose. Okay, and of course, if instead of going here I had gone somewhere else, you could have done a similar thing and still won. Okay, so this is not very interesting either. But what happens if we take larger boards? Well, of course, the first player is still going to win because, well, you just repeat the same strategy. But now, what if you take a larger board and you also say that to win, a player needs to put more than 3 in a row? Okay, so this is a natural generalization. So people have looked at this problem, which is called basically the MNK problem. And the MNK problem is the problem where you play on an M by N grid, and each player is trying to put K symbols in a row. So either in a line, in a column, or on a diagonal. So we're going to look at this today, and we're especially going to look at the case where M and N are actually infinite, so we're playing on an infinite board. All right. So, first of all, let's show that only the first player can have a winning strategy. So to do this, we'll use a classic argument in game theory, in combinatorial game theory, which is called strategy stealing. So basically, suppose that player 2 has a winning strategy. So if player 2 has a winning strategy, well then basically player 1 can copy his strategy. How does player 1 do so? Well, basically, let's say player 1 plays his first move anywhere on the board. Okay? Well, then player 2 is going to play a move. Okay? Which is part of his winning strategy. Right? And now, player 1 is going to play the move that player 2 would have played if player 1 had played here. Okay? So basically, player 1 is going to do as if he were player 2 and play the winning strategy for player 2 as if he was going after. Okay? The only difference is that he has already placed he has already played once. But basically, this doesn't change anything because why can he repeat player 2's strategy? Because either player 2's strategy involves playing somewhere that is not here, and then player 1 can just copy it, or player 2's strategy involves playing here, in which case, well, player 1 can just choose to play anywhere else instead, as since this tile here is, well, he's already played on it, well, any winning strategy from player 2 that uses this tile, well, will also be a winning strategy for player 1 using this copying argument. Like basically, since he has already played here, well, he's fine. He can just play anywhere else if need be. Okay? So by copying player 2's strategy, well, actually, we show that if player 2 has a winning strategy, then player 1 also has a winning strategy, which is, of course, a contradiction. So player 2 cannot have a winning strategy. Okay, but of course that doesn't mean that player 1 must have a winning strategy. Of course the game can be a draw, as is the case in the regular tic-tac-toe. So we've seen that on larger boards, when you're playing 3 in a row, then player 1 is going to be able to win. If you play a bit with even larger boards, you can show by just testing out different cases that you can actually find a winning strategy for 4 in a row. So the first player is going to be able to place 4 in a row if he's given a large enough grid. And then for 5 in a row, actually the result still holds, but in that case it's much easier to show, and you definitely won't be able to do it by hand. In that case, computers were used actually to show that the first player could place 5 symbols in a row. Actually, it was showed, just a little piece of information, it was showed for 15 by 15 boards. So on a 15 by 15 board, player 1 will be able to force a 5 in a row. Right, and why was this board studied in particular? Because this game, doing 5 in a row on a 15 by 15 board, is called Gomoku. Okay, and so it was conjectured for quite a long time that this game was actually a winning game for the first player, but it was only proved proven rather recently, thanks to the use of computers. Okay, so now let's look away from finite boards and let's look at the case of infinite boards. Okay, for how many tiles in a row can the first player be able to place on an infinite board? Well, first of all, it may seem that if you take a very large board, then the first player can actually place arbitrarily many points in a row, but this is actually not true. And to show that this isn't true, the classical argument is the pairing argument. So how does the pairing argument go? Well, basically, you're going to cut up your grid. So let's say you have an infinite grid. So let's just draw a part of the grid. To do a pairing, you're going to cut up the grid in small subparts of the grid. So let's say this one, this one, this one, this one, whatever. And in every one of these parts, you're going to pair up the tiles. For instance, let's say this one is paired with this one is paired with this one, and we do the same thing for the other subsets. Okay, we do things like this. Okay, and usually you have a pattern in a subset that repeats, so over the whole infinite board. And basically, what is player 2's strategy to draw? Well, every time player 1 plays in one square, player 2 is going to play on the related square, the square that is paired up. Okay? And so basically, if one can find a pairing here, such that there are no lines of k in a row that do not include a pair, well then since every line includes a pair, well that means that player 1 cannot win the game, because by using this pairing strategy, player 2 will always block player 1 by using the paired squares before player 1 manages to get his line. Okay, so now just a quick concrete example to show this into application. Let's take a slightly simpler version of tic-tac-toe in which a player can only win by doing k in a row on either a line or a column, so without taking into account diagonals. And we'll see that in this case, well, pretty quickly actually the game becomes a draw. Right. So let's look at a 4x4 grid. Okay, and we're going to construct the pairing in this way. So let's say we take here 1, 1, 1. So these two squares have the same number. That will mean that they form a pair. Here we can do, I don't know, 2, 2, 3, 3, 4, 4, 5, 5, 5, 6, 6, 30. Wait, let me just switch this up. Let's rather do 2, 2, and 3, 3. As such, okay. And then 7, 7, and 8, 8. Now, I claim that by using this pairing strategy, player 1 can never place 5 tiles in a row. Why is it so? Well, because look at every line and every column. We said we're not looking at diagonals. Well, notice that every line here in this 4x4 grid contains a pair. Here it contains the pair of 1s, the pair of 4s, the pair of 7s, the pair of 8s. And same for every column. This column has the pair of 3s, this one the pair of 2s, this one the pair of 5s, this one the pair of 6s. Okay? So that means that player 1 can never achieve a position in which he occupies an entire row or an entire column. For instance, he can never achieve this because when he places here, well, player 2 is going to play here, and when he plays here, well, player 2 is going to play here. So this can never happen. Okay, so now, well, basically what you can do is you can extend this grid to basically see what's going on. For instance, like here I have the same grid, which I number in the same way, so 3, 2, 1, 1, etc., etc. Right? And here you see that, well, for instance, player 1 can never achieve, so this square, this, well, no, wait, not this square, but he can never achieve this square, this square, this square, this square, and this square. He cannot achieve these 5 squares in a row. Okay, so basically we can look at the overlaps between our grids, right? Because our grids, in the end, they will cover the whole plane. And so if we can just show that there can be no sequence of 5 which doesn't include a pair, well, then we'll be done. But now notice that, well, since these pairs here, every time they're like dominoes, basically the pairs are always made up of adjacent squares. Okay, well, actually these adjacent squares here Well, what is the distance between these adjacent squares and the adjacent squares in an adjacent 4 by 4 grid? Well, the distance is exactly 4, right? Because this pattern repeats. It repeats infinitely often over the plane. So here we have a distance 4. Okay? So necessarily, if we have well, five aligned squares here, well, they must cover one of these two pairs. Yeah, like for instance, if I start here, I'm going to have to cover this one, and if I start here, well, I cover this one. Okay? And so basically, yeah, the fact that this pattern repeats and that these squares are close together, they're like dominoes, shows that, yeah, we cannot align 5 squares without encountering a pair. Of course, it's the same thing if you work vertically. Okay, so we've shown that this tic-tac-toe variant is a draw when there are at least five tiles that you need to align in order to win. And actually, in this case, I'm not sure if the case where you need to align 4 is a draw or if it's a win, because it's definitely a win in the original tic-tac-toe, but in this variant, I haven't actually looked at it. So feel free to try and study that case. Okay, so now let's go on to the more complex case where we actually take into account diagonals. So notice that the previous construction didn't work because we could very well have some very long streaks over diagonals that do not encounter any pair. So we need to put our pairs in such a way that every diagonal of sufficiently long length contains a pair. And this is actually not so simple. If you start playing out with some grids, you realize that you need some pretty large pairing grids, let's say, to achieve this. And I was looking at this problem and trying to find a pairing pattern that would work, and I realized after a bit of time that quite naturally I was going to study an 8 by 8 grid. Why is that so? Well, because think about all the pairs that you need. Okay, you know that let's say you're looking at a subgrid. Okay, you're going to take a square subgrid. That's what makes the most sense. So a subgrid of size, which has n times n squares, and you're trying to create a bunch of pairs in this grid such that every line of the grid contains a pair, every column and every diagonal. Now notice that when we look at the diagonals, we're not only looking at the long diagonals, we also need to look at this diagonal, for instance, which is not as long as this long diagonal, but let's say, we can imagine that it goes on afterwards or before. So we need to be careful about these diagonals, and so it's good to have pairs on the diagonals as well. Also notice that if you have a pair on this diagonal that's adjacent to this one, well then you don't need to have one here, right? Because here, well, this spot is the same as this one, just on 2 adjacent squares, right? So like if you got a pair here, well, it's going to take care of this streak, which is also taking care of this small diagonal over here. Okay, so we only really need to look at diagonals that are like this, and also going in the other direction, so like this. Okay, and now if you quickly count how many such lines, columns, and diagonals you have in this n by n squared grid, well, you have n lines, n columns, you have n diagonals going, let's say, left to right, going up. Right, since we don't take these ones, we said that they're already taken care of. So n diagonals, let's say, going up, and n diagonals going down. Okay, and so for every one of these objects, we'd like to have one pair inside our square grid. So this actually forces our square grid to be quite large, significantly larger than the 4x4 square grid that we studied earlier. So here, how many elements we need? Well, we need 2, so 2 because a pair is made up of 2 elements, so 2 times 4n, so equals to 8n. Okay, so we must have n squared greater than 8n, which gives us n greater than 8. Okay, so it makes sense to look at the 8x8 grid because it's the smallest grid where you can hopefully build a pairing that is rather simple, right? Where you just try to find a pair on every line, every column, every diagonal. So that's exactly what I did. Okay, and if you spend a bit of time doing this, if you just start building your pairs, well, after a bit of work, you realize that you can actually find a pairing. You can find a pairing of the 8x8 grid where there's a pair in each of these elements. And so what bound does that give us on the number of aligned elements such that tic-tac-toe becomes a draw? Well, it gives us a trivial bound of 15. Why does it give us a trivial bound of 15? Well, quite clearly because if you had 16 aligned squares, well then either they're aligned in the shape of a line or a column, in which case, well, they must contain in some subsquare, they must contain all 8 of these, and hence they must contain a pair. Or if they're on the diagonal, well, once again, well, here it's slightly harder to visualize because, as we said, this diagonal, right, when you go in the adjacent square, well, you're basically coming out here. Okay, so you need to look at pairs that are potentially here. Well, even though in this case we constructed the pair to be here. But in the same way, your diagonal will have too many elements. That are lying in this square, and once again you'll be forced to encounter a pair. Okay, so that's if you have at least 16 aligned squares. So hence, tic-tac-toe is a draw for k greater than well, for k greater than 15 actually, because okay, here you might think that with 15 we can manage to completely avoid a line or a column or a diagonal, but of course we can't. I said that with 16 we can't avoid them, but also with 15, because with 15, well, for instance, on a line, well, you're forced to have all 8 elements on one grid, plus 7 elements on the next one, or 8 and 7. But you can never have 7 and 7 because you'd have 14 here. Okay, for k greater than 15. And actually, I'm pretty sure that in my proof, the pairing was constructed in such a way that this was even shown for k greater than 14. Okay, you just look at the pairings and show that there can be no long streak of squares which avoids any pair. Okay, so this is a first, let's say, simple bound that really doesn't require much intuition. It's just quite tedious. But researchers over the years, well, with these pairing arguments, they found some more refined, some more subtle pairings, sometimes in smaller squares, but not necessarily having the condition of one pair per line, column, diagonal, but looking at these overlaps, well, one could always show that long streaks of squares would end up encountering a pair. Okay, and by doing these quite sophisticated pairings, they managed to show that tic-tac-toe is a draw for k actually larger than 9. K larger than 9. And actually, you can find on internet the construction of the pairing that shows this fact. It's quite nice. I mean, it's just not very simple to come up with such a pairing yourself. But of course, it's not very hard to check that such a pairing works. So yeah, this was constructed I think in the 60s, something like that. But this is not actually the very best bound that we have obtained on this problem, right? This problem of finding the minimum k such that tic-tac-toe is a bound, is a draw. Sorry, because actually this has been shown also for k equals 8. But show k equals 8 actually. Pairing arguments were not used. Another argument was used, which I'll probably discuss in the next video because it's quite nice. Okay, so tic-tac-toe was shown to be a draw for k equals 8 on an infinite board, but what about k equals 7 and k equals 6? Right? I said earlier that k equals 5 was a win. That was checked by computer. But what about k equals 6 and k equals 7? Well, we don't know. We don't know. There has been a lot of computation that has been expended to try and solve these cases. Well, we mostly believe that these cases are draws, right? Because it was already very hard to find a winning strategy when k was equal to 5. So most likely k equals 6 and k equals 7 should be draws, but it's just hard to find a structured strategy for player 2 to actually force the draw, right? Because here every time the strategies that we show with the pairing, or even when k equals to 8, are quite rigid strategies. They're not strategies that a human would play. They're not very flexible strategies. So of course, well, it's going to be hard to find such rigid strategies in the cases that are close to being winning. So yeah, these questions are still unsolved, which is pretty interesting, I thought. And maybe next time I'll also talk about some generalization of tic-tac-toe, like in 3 dimensions or in arbitrary dimension, because there's an application of the very well-known Hell's-Jewett theorem in combinatorics, which is also something I recommend you go and learn about. And so yeah, tic-tac-toe has some pretty cool facts about the math and combinatorics that are going on. And that's it for today.